Hello guys, you're welcome to this lecture. I'm going to go through matrix exponentials. The lectures are going to be a bit short, maybe 10 minutes, 15 minutes thereabout, to reduce the size of the files. So what I'm going to do is I will go over some things that we have already done in class concerning the matrix exponential, and then I'll proceed from where we stopped or where we left off for the break, and then we'll continue from there. So every week I will try to post some videos and slides that will accompany it, as well as you have the lecture notes that you can go through. So basically these slides are from the lecture notes, so you can go through the slides. You can also look at the lecture notes. It should be the same things. I'm hoping that these videos will sort of augment or help explain some of the things that are in the notes. Okay, so for this lecture I'll go over the introduction and motivation for the matrix exponential. We'll give a definition, of course, of the matrix exponential and how you compute the matrix exponential. We said that it is involving, if you want to just compute it straight away from the definition, but it's a little easier if A in your system of equations, the matrix A, is a special type of matrix, like a diagonal matrix or a nilpotent matrix. And so we'll look at the special cases, and then later on in some other lectures we'll look at the generalized, so-called generalized eigenvectors. And then much later we'll look at an algorithm known as the Puza algorithm, which you can also use to compute the matrix exponential. At the end of each video lecture, I will try to post some exercises that you can take a look at. Okay, so here's an introduction. Consider the system x prime, because x as a vector. This is a matrix, of course that is a vector as well. And now if you follow the approach for a linear equations, you can assume a solution of the form u to the power rt multiplied by a vector u. We are going to assume this is a solution. If it's a solution, then it must satisfy equation 1. So you can plug this into equation 1 and manipulate it, and you get this. You can rewrite e to the rt cancels out. You have this. Take this to that side of the equation, and you are left with this expression a minus ir multiplied by u equals 0, where I here is the identity matrix. Okay, good. Now we have encountered this before. What this means is that this equation here, x is equal to e to the rt times u, is a solution to the system for if equation 6 is satisfied. In other words, if I can find an r, which we call an eigenvalue, and a u, which we call an eigenvector, such that this combination is equal to 0, then I have a solution which is given by equation 5. Okay, so we've seen this before. Now, if A is not symmetric, we mentioned this also in class, it is possible for the system to have repeated eigenvalues, but not to have two linearly independent eigenvectors. So for example, this matrix here, you can go through the procedure of finding the eigenvalues. You find that the eigenvalues are repeated, -1, but if you find the corresponding eigenvectors, you only get eigenvectors that are of this form. U is equal to s times 1, 2. Okay, so these are the eigenvectors are not linearly independent. The question is, how do you find a second linearly independent eigenvector when you have one of them? Well, in the case of a 2 by 2 matrix, we know how to do that. we have encountered this before. So in the case of 2 by 2 matrix, we said that what you do is that once you find one of the eigenvectors, so if you put s is equal to 1 here, for instance, you get an eigenvector. So once you get one of the eigenvectors, you can find a second one, call it w, by solving this equation. So solve this equation here, and then you get a second linearly independent eigenvector, which is W. All right, so it's all nice and fine when your matrix here is a 2 by 2 matrix. So we are moving to the realm where A is not just a 2 by 2 matrix, but it's just any n by n matrix. If you have repeated eigenvalues, how do you deal with that? How do you find a solution of a system, say by 3 by 3, right? It's 4 by 4, 5 by 5. How do you do that? So that is what we are moving on to. Now, to do that, we need what is called a matrix exponential. So that is why we are studying that. And then we also need to use what is called generalized eigenvectors, and these will help us to be able to solve general systems, not just 2 by 2 equations. So here's a motivation. If you have a first order equation of the form, this is not a system. This is just the linear equation. You have x prime is equal to dx to t. X prime is dx to t, and that is equal to alpha x. Alpha here is just a constant, then the general solution is given by this, some constant times e to the alpha t. All right, so this is straightforward. We did this in chapter 1. So the motivation for using the matrix exponential comes from seeing the similarities between this equation and a system. Okay, so this one is a system, it's a vector, it's a matrix. If you look at this, it resembles that, and so you expect that a solution to this system will also look somehow like this, where in this case alpha is no longer a constant but is a matrix, and then this c is no longer that's constant but rather a constant vector. All right, so that is the motivation for saying that there must be this entity or this this thing e to the at called a matrix exponential that will help you to find a solution to a system 7. Okay, so that is called a matrix exponential. We'll define it shortly. So from here onwards, instead of using bold, we are going to be dealing with systems. So whenever you see x, whenever you see a or c, just assume that it's a vector or it's a matrix. All right, I'm not going to be bolding them anymore. Okay, so here is a definition of the matrix exponential. Suppose you have a matrix, an n by n matrix A, then e to the at is given by this series. Okay, I here is the identity matrix. You have a multiplied by your t, a squared, t squared over 2 factorial, and so on, which you can shorten to this. So basically that is a definition for the matrix exponential. So this is why it's a bit difficult to compute the matrix exponential from the definition, because note, a is fine, but you need to compute a squared. Assume a is a 4 by 4 matrix. You need to compute a to the power 3, and so on, if a is a 5 by 5 matrix. So that makes it much involving, and so that is why we have to go through some techniques for how you compute the matrix exponential, because once we have a matrix exponential, then we are guaranteed to have a solution to the system. Okay, so first, before we learn how to compute the matrix exponential, what we are going to do is write down, we have looked at some of these properties of the matrix exponential. We'll go through a few of them, and then we'll apply them as we go along. Okay, so we are going to state it as a theorem. We'll not prove all of them. Some of them are quite easy to prove, others you can try your hands on them. So let A and B be n by n contract matrices, and R and S and T are just real numbers or complex numbers. Okay, they are not matrices. Then e to the a0 equals e to the 0 equals I. In other words, just plug t equals 0 here, for instance. Actually, this is not bold, it's just 0. Into the definition for the, if t is 0, all you have is I. All right, all you have there is I when t is 0. All this goes to 0. So this one is straightforward, and this says that e to the a multiplied by t plus x is equal to e to the at multiplied by e to the as. Okay, this says that the matrix exponential has an inverse, and the inverse is given by this quantity here. So to find the inverse of the matrix exponential, all you do is that replace t with negative t, and you get the inverse. This says that e raised to the power a plus t, a